Dat is refresh.
Er zijn heel veel mensen die zeggen dat dit zijn ja, ik heb
Too late. Ja, ik heb er zelf een beetje thuis al gevoeld. Ja, toen ben ik met nee, maar Mag ik vragen?
Ja,
De titel, er staat lecture 4, maar het eerste woord wat erachter staat, weet ik niet wat er staat. Dia. Kijk, dankjewel.
ja, dankjewel. Het is altijd zo gestrest om een heleboel werken te krijgen.
Ja.
En dan zit ik eigenlijk zo te schrijven.
Ja, snap ik.
Into Okay, let's do an early start, 30 seconds before the regular time. I get a cue here. Somebody's giving me the cue. Is the recording started? And okay, now I help remember you instead of the other way around. Okay, welcome to the fourth lecture. The topic of today is adding passive and active elements to our system, because until now the system was pretty boring, rigid bodies with constraints, and I mean, how does it move? So we need movers, and we need storage, and we need dissipation. And we're going to treat impact equations, because in a lot of applications you want to idealize sudden contact. I mean, you can calculate it as a function of time, but impact is a nice idealization of a sudden impact. And applications are dynamic walking or whatever. But of course, we start with the in-class quiz. So let's see. Let's make this small. Then we go to how do we log in? Well, the most important one is, of course, to enter a PIN and enter as your nickname. Put a number in it, and the number should be your student ID, so that should work. Huh? I still get participants who log in with a name and no number. I mean, that's nice, but you cannot get any grade. Huh? That's clear. Okido, Kahoot. Quiz number 4 this year, yes. I'm gonna do something. Okay, let's make it big. Yeah, classic. We like classics. Go out. Now start. Yeah, of course. Stupid. Isn't technology great? I mean, it's, every time I'm amazed, really. Wow. Yeah. Yeah, it's around 176, something like that. Sometimes somebody has the flu, or they. Yeah, me too. Okay, 176. Let's start a quiz, right? You ready? 5 questions. And since the enormous success of last week, again, people in the live stream, you have a 10 seconds delay, so answer please. Okay, so that was not so hard. Let me check the camera. How was it? Oh, pretty good score. Okay, Roelof. Roelof in the audience? No. This is about kinetic energy in a system. But actually it's about index notation and Einstein's summation convention. Sort of a mixture question, right? It's all about getting your indices right. Or left. You do have lecture notes, right? Oh, heb je het al gehad? Oké. Ah, ja. Dat is Fred, hè, denk ik. Oh, ik het. Ja. Yeah, okay, I'm happy. So almost everybody is up to speed with their index notation and Einstein summation convention. Okay, let's move on. Rule of again. How many degrees of freedom has the system in this configuration? Okay. Okay, let's discuss, right? Because when I look at the answers, the majority, of course, is right. Mechanics is about democracy, but there's a large number of people who vote for 1 degree of freedom. And if you just do counting, you probably come to the conclusion, oh yeah, it's 1 degree of freedom. But however, if you put the system with no velocity, with no motion, in this configuration, then actually there are 2 types of motion the system can have. It can continue like the picture above, or it can just rotate about the origin. So it has essentially 2 degrees of freedom. Now I had to put at rest there because if the system is moving, it's very difficult to move from one mode to the other mode. So therefore I technically had to write at rest, which may be a bit confusing for some, but it's a deeper technicality. Okie doke. And the mathematical thing here is of course that the constraint equations are dependent. You have 4 constraint equations, you have 4, no 5. You have 5 constraint equations and there's a dependency in those 5 equations. And that is the mathematical background of the whole thing. Okay, let's move on. We have a new winner. Nameless, anonymous. This is about Lagrange multipliers and how can you identify them in the system. So this means actually that I did not do my job very well, apparently, right? If the score is so low, then either the question is wrong, but that's not true. The question is correct, but apparently I didn't explain it well enough. In the lecture notes, there is a problem, a worked out. Now, then I think it's an example where it's exemplified what the relation is between forces and Lagrangian multipliers. In the case, it's a point mass on a parabolic line, and if you study that, then you will understand why this answer. The answer was this one, the correct one, is the correct answer. So please study lecture notes, and maybe we come back to this next week. Who knows? Okay, last question. This is about the topic of today, energy loss during impact. Okay, let's look at the problem again. Apparently there are two popular answers, something with v squared apparently, and the correct answer. So let's look at the question again. There are two concepts here. One concept is the impulse, the contact impulse, and impulse is momentum, it's mass times velocity, and the relative velocity before impact, v minus. And then there's a coefficient of restitution, which is not so important, I guess, for the question. Now, if it should be energy loss, then the dimension of the result should be energy. And of course, a lot of students then say, oh yeah, v squared, that's energy. Yeah, well, almost. M times v squared is energy, right? So for a unit mass, yes, but for the mass here of the system, which is some number. So dimension-wise, this cannot be true, the blue answer. Think about Heike. Heike always says, oh, check your dimensions and so on. So, and this one, p squared, for the same reasoning, dimension-wise, could not be true. I mean, mass times velocity squared, you get mass squared times velocity squared. That's a lot of mass energy, right? So, the only correct thing to get energy is momentum times velocity, or impulse times velocity. And then we have two answers. And what is the difference? I don't know. Oh, 1/2, yeah. For some reason, with energy, you often come up with velocities and 1/2. And yeah, I know a little bit why, maybe, but we will see later on. Yeah. So apparently the 1/2 is the correct one. Okay, that was it, I guess. We're 5 questions. We're done. Yeah, I'm gonna get the result. Save it. Please give me some feedback. That's always helpful. Yeah, and save it to the drive. It's also helpful. Save, that's good. Okay, discuss very show the feedback. Yeah. No, a little bit less than last week, but well, the questions were also a little bit more serious this time. In the beginning, it's a little bit playing around, but well, it's getting more serious. The whole contents also of the course, so therefore, the questions are also more serious. Thank you. Okay, the stream is working again. Still, I make this smaller. I go back to my air server. I make this large. And then we go to the lecture of today. Okay, so I'm going to add passive and active elements. Now, first let me be clear, what do I mean by passive and active elements? For instance, a passive element, an example of that one is something like a spring. So we can connect springs to our system. And if I think of an active element, then I think of things like motors. And I like electro engines a lot. So you have 2 wires here, and then you put an alternating current in it, and then wow, you get a speed here and a torque, and you can drive anything. Machines or bicycles, or even with electromotors you can do Teslas, for instance. So those are the two types of elements we like to add to our system. And as an example, I'm going to take just the double pendulum, and then just part of the double pendulum, and I'm going to add a spring to that. So I'm going to add it to the first body. So this is the first body with a center of mass here, and of course after that there's the rest, but that's not so important for now. The thing is attached to the ground in A, if I remember well. Yeah, and this is point 1. We need a coordinate system according to Heike. Yeah, and then we're going to add a spring. Now, where do we do that? So there's some point D on the body, a fixed point on the body, D, and then there's some fixed point in space here, and that's just for simplicity, because the spring can also act between 2 bodies, of course. And then between that, I'm going to make a spring, like this. And then the spring, well, looks a bit quirky, but it has some stiffness K, and it has some rest length, which is in this case equal to the length of the bar. And this was the length of the bar. Now, where is the spring connected? And point D is at the distance of 2/3 L. And the point above, which is E from echo, the height for that one is L/2. Okay. And then for the spring, we write here at the spring some stiffness and an initial length. Actually, what we mean is if you take the spring like this, and this is like the rest length, L0, then you can elongate the spring over a distance delta L, and if you do that you get a force which is proportional to that elongation. And the rate of proportionality is then called stiffness. So the spring force is K times delta L. And then I have to define what is delta L. Well, delta L is the length of the string minus the rest length. This law is connected to which scientist? Hooke. I can really advertise to read a biography on Hooke. He's a remarkable figure. Fellow of the Royal Society after a long time.
I don't think Newton would agree.
Well, I disagree again with that statement. So somebody knew how to say Newton doesn't agree. Well, Newton was fighting with everybody, so that was sort of biased in that sense. But Hooke had a hard time being acknowledged as a real scientist, and there was always a lot of dispute about originality. So is it my law or is it his law, or did he discover it or did I discover it? Also, one of the reasons why I want to put for you to put in that academic integrity thing, right? To get rid of all these discussions. Okay, back to our problem. So how do we incorporate such a spring? Well, there's one big mechanism or system we have, and that is our virtual power. Because through this virtual power we can connect everything. So the virtual power of our system was initially, we had our applied forces, Fi, we had our mass terms, our D'Alembert mass terms, and for now let's forget a little bit about the constraints for the moment, or we can say, well, yeah, it's for all velocities which fulfill the constraints. So, done. And then we say, well, is this all the virtual power which is in the system? Well, actually not, because if you add elements, these elements also have virtual power. So let's look at the extra virtual power due to the elements. Extra virtual power due to the extra elements. Now, for instance, the virtual power of that spring is, well, power is force times velocity, right? So it's the spring force, Fs, and the velocity is the delta L with a dot. So the elongation rate, and then we make virtual by this strange delta. And actually, what we now do, if we want to look at the complete system, then for the whole system, the complete system, we just add, we say, well, we have to take delta P plus delta PS, right? And the plus we do in a bit of a strange way. It goes like this. We say, well, our new virtual power expression, delta P star, is now the old one, the Fi minus the Mij, x double dot j, virtual velocities of all the center of masses. And then I add it with the minus sign, and the sign is actually just a convention. It's a sign convention, and it has to do with that if you pull on a string, you have a tension for an elongation, but it's just a sign convention. In the end, you have to get your sign such that if you push to an object, that it will move in the direction which you push. If it moves in the other direction, you have to flip the sign. Yeah? So this is Fs times delta dot. And of course, we say the system is in equilibrium. So this is the equilibrium statement. Is 0 for all, and then again, the virtual velocities should fulfill all the constraints. All the joints should stay together. Now, if we look at the variations or at these virtual velocities, here we have a virtual velocity expressed nicely in the center of mass coordinates, but here we have it in this elongation of the spring. So the next step we have to do is we have to express this elongation of the spring in terms of the center of mass coordinates, so xi. Which we can do. I mean, if you move the bodies, then apparently the spring will elongate. And if we can do that, so let's assume we can do that, then of course you can determine easily that the delta dot L is of course is delta L comma I x dot I. And then we are in business, because then we can substitute that in that equation. But our first step is now to express the elongation of the spring in terms of the elongation of in terms of the center of mass positions of the body. So therefore we have to redraw our figure again. Well, the nice thing is I don't have to redraw it here. You can do a magic marker, something like this. Copy. And go down. And down. Here. There. Yeah. Good plenty. So here we have our, we can make it a little bit smaller. Okay, so now can we express the elongation in terms of the center of mass coordinates? Well, if we want to calculate what is the current length of the spring, so this distance, this is this L of the spring. No, that's not this. The length of the spring. Yeah, maybe I should do an S for. To add an S somewhere here. Yeah. Okay. So if we want to calculate the length of the spring, then it's pretty easy, because the only thing we need is the two coordinates of the two endpoints of the spring, and then we just take the norm, and then we have the length, and then we're in business. So the length of the spring is easily expressed as the norm of these positions, xd minus xe. And those positions are also easily calculated. xd, the x position of that is starting from body 1, of course. So, what is it? x1 plus, now we need this small distance here. That is 2/3 minus 1/2, and that's 1/6, right? Yeah. So 1/6 L, and it's the cosine of phi 1, right? What is wrong with the sign? Okay, maybe because my notes were on my computer. Can you ask again to check? Let me see, OBS. Yeah, maybe my notes were on my computer, and therefore it was obscuring the mic, and so yeah, I'll do it like this. Oops. Hopefully better. Okay, so this is the horizontal position, and the vertical position is y1, of course. Oh, yeah, sorry. Yeah, technology is, and let's enlarge it. So this was the horizontal position of point D, and then the vertical position is the same, but then with the sign phi, right? And point E is actually pretty simple here, because that's a fixed point, 0 coordinate, and the y coordinate is L/2. So calculating the length then of the spring is taking the square root of, well, we have to subtract the x's, so that is actually x1 plus L over 6 cosine 1 squared, because there's a 0, and then plus, and then the y coordinates are y1 plus L over 6 sine 1 squared minus L over 2. No, not the squared. I fixed it. I can do it. Put it over there. So then we have the length of the spring. But the point I want to make, and then of course the elongation of the spring is the current length of the spring minus the initial length, which is in fact the same expression minus L, the length of the bar. But the point I like to make is that delta L is just the delta L expressed in our coordinates xi. You can always, whatever the system is, you can always express this length as a function of all these displacement of the bodies. And we're going to generalize that. We're going to say, well, this delta L, I'm going to call CL. It's not a constraint. It's because it's not going to be 0. So CL is now what I call delta L. And then my delta L dot is of course simply CL, I x dot. And now I'm able to put that expression in my virtual power expression, so I get delta P star equals, and again, Fi minus Mij x double dot j, virtual velocities I, and then minus, then we had this spring force, then we get this CL, I times my delta. Well, the L is a bit stupid. Maybe I should have called it an S, right? In complete accordance with the spring force. Yeah, let's call it S. Of course, it's just an index. It doesn't matter so much. So now you can have S springs. On top of that, of course, we like to add our constraints, plus our constraints. And the constraints, remember how we incorporate that. So our constraints were this form, Ck of xi is 0, and then by means of this Lagrange multiplier, lambda k times c dot k, we incorporated that, we added that to the equation. So I take again this one, copy, and then now with the constraint, and then with the constraints, I'm going to say, and how do we add them? We use the minus sign there too, right? Minus lambda k, and then ck, comma I, lambda dot I. And this now holds for all virtual velocities as long as they're not all 0. And if it holds for all virtual velocities, then I finally get I equations. So my equations of motion with the incorporation of all these elements now breaks down to the following. And yeah, maybe I should reorder the terms. Well, maybe not for now. First we'll write it down. So Mij x double dot j, then minus Fs Cs, comma I. Those are the active and passive elements. Then minus Cky, this lambda k is 0. Now, what are the knowns and what are the unknowns? So usually, so let's say unknown guys are, well, we don't know what the accelerations are, right? Do we know what the spring forces are? Yes, that's the fun of it. So these elements, for these elements, it's given what the forces are. For a spring, it's the spring stiffness times the elongation. For a motor, it's the amount of voltage or the regulation you put on. So that force is given, it's not an unknown quantity. And the Lagrange multiplier, of course, we don't know what that number is. Those are our joint reaction forces. So these are the unknowns. So now I'm going to reorder the equations a little bit and write them in the order of unknowns on the left-hand side and knowns on the right-hand side. So we get Mij x double dot j, and with the same sign we get plus Cky lambda k, and then on the right hand side we get our applied forces minus our Csi times Fs.
But CSI is not a known. If you take the Jacobi reductive binding elements of phi, and if you don't know phi, CSI is not defined in terms of the coordinates of the sensor of
Absolutely it is. Let's go back. CSI is the elongation of the bar of the spring. And the elongation of the, it's the elongation of the spring. The elongation of the spring I can always express in terms of center of mass coordinates. Think in a physical way, like, oh yeah, where the bodies are, I can always calculate. So, conclusion. If we write then the complete equations, of course we have to add our constraints. So Ckj, x double dot j equals minus Ck ij x dot I x dot j. Yeah. And then I always like to write them in this nice pseudo matrix vector form to just see what is going on. It's a sort of a strange notation. But you clearly see what are the unknowns and what are the known vectors. So this is the first equation, the right-hand side applied forces, and then these for the active, passive or active elements. And then the last equation is of course our constraint equation, a lot of zeros, and then here minus Ck. Now if we compare this to our result from last week, then the only difference we get is this part, right? So this part is where the passive and active elements pop up. And so the forces of the extra elements, are transformed by CSI to the CM forces. So Fs. So we have element forces. In the case of a spring, it's the force along the spring. But for our equation of motion, we always need to express our forces at the center of mass. So we need to replace them to the center of mass. Now, this replacement to the forces of the center of mass is done automagically. Again, we have this automagic thing by this Jacobian. So again, let's draw a sort of a free body diagram, sort of, because otherwise I get Heike on my neck. So the only thing I now cut loose is this spring. So here we have this spring force. And the big question is, this you should translate to the case where all the forces are at the CM. So here we have an Fx, we have an Fy, and we have a torque. And my statement is that that is automatically done by this CSI. That's the beauty of the whole mechanism of this virtual world. Or in other terms, the forces at the center, the forces here at the center of mass are identical to minus, and it's again a sign convention, identical. How are we doing on time? Yeah, okay. Let's take a 15-minute break. And then in detail we're going to look at, well, how does this work for this exam?